Back in 1978, that growing season might have started on October 18th and started on April 26th and extended through October 18th. Now, that same growing season may start as early as April 4th and roll through the end of October. We've had last first freeze dates in the fall happen as late as November on some of these. And so that's showing how the seasons are starting to shift. We've seen accumulated growing degree days going up. That's not a surprise since temperature is going up, so these are the growing degree days in Fahrenheit. We've even seen some really interesting kinds of events, so I like to point out the summer that we had in March of 2012, where we had a fairly extreme heat event in March. This is the temperature trajectory for the whole month. And we had these 2 weeks of really high record temperatures in March that got close to 80 degrees. I was out fishing Penn's Creek actually during that time frame, and I couldn't believe how warm it was for mid-March. And that long heat spell actually had a lot of plants started to bud, or the trees were budding, fruit trees were budding in response to all that heat, that early spring heat. And then lo and behold, at the end of the month, we got 2 days of really hard frost, and that caused quite a bit of damage throughout not just Pennsylvania, but most of the northern US. The American Geophysical Union had scientists look at this event, and they said it was the earliest spring in the North American record. So it's the earliest, probably until February 2017 was the earliest. And that frost that happened late at the end of the month caused all kinds of fruit tree damage, including in Pennsylvania, throughout the Northeast. A lot of damage areas were damaged and were declared disaster areas. And so there's a risk of these late season frosts, especially when you get these warm springs. And it looks like that risk, at least for the near term, remains. That there's always going to be this risk of an early spring and then potentially a late season frost. But the climate models, like when you look forward in time, they project that these fall springs are probably going to be occurring less frequently, and the risk of frost will start to diminish. But maybe the next couple decades, next decade or so, these kinds of events are still out there, and their potential for them to occur is real. So in terms of watershed hydrology, like just looking at stream flow and rainfall, how are these things changing? So I'm showing these trends in inches. So the way we convert stream flow to inches, stream flow is measured as a volume, but we divide by the watershed area. That gives us a depth. So you take say cubic feet and divide by feet squared, you get feet, and we can convert that to inches. And so that's how I'm able to show stream flow as a depth in inches and compare it to rainfall. So here's our precipitation trends. These trends are not significant. Rainfall is going up, but it's not a significant increase. That means it's not statistically significant. So there's a slight increase in rainfall. What we have seen is a bigger drop in stream flow, but it's also not significant. But the interesting thing is, that divergence, with rainfall going up and stream flow going down, actually yields a significant trend in evapotranspiration. So what we see is an increase in watershed evapotranspiration. That's just water use by plants. That's just inferred by difference, by subtracting the amount of rain that we get in versus the amount of water that comes out of the watershed. So by difference, we can calculate ET, and this is not surprising given that the growing season is getting longer, plants are transpiring for longer periods of time. That means they're removing more water from the watershed, and we're losing it as ET. These trends have been seen elsewhere throughout the Northeast, although there are some places that are showing drops in ET, especially in the forested parts of the Northeast. And so there's not 100% agreement on the direction of these trends, but most watersheds have seen an increase in ET. Oh, I'm sorry, you have a question.
Couldn't that also relate to improved infiltration?
With an increase in evapotranspiration?
Or the reduction in stream flow with the same amount of rainfall?
Well, there's just, we have less moisture, I guess, that the soils won't be as the trees are using more water, or for longer periods of time, really, is what it is. I mean, because the growing season's longer, they're able to use, water extending through the fall when they might have shut down a little earlier. At least that's, one of the explanations for the increase in ET. There's also been an increase in greenness too, which we don't have those kinds of data, but I've seen them in papers where they assess with remote sensing just the greenness of the landscape. There could just be more stuff growing too, and using water more intensely during the growing season. So there's the expansion of the growing season is one thing, and the intensification of vegetation, in response to warming weather, could also probably play a role. As far as infiltration is concerned, I mean, it's kind of probably driven more by the soils, but certainly if the soils are wetter, they can't take as much water than if they're drier. So if you're drying the soils out, perhaps they could take more water in a given storm if there's less water available in soil storage. So that could maybe be, what you're asking. Oh, for sure, yeah. I mean, that's one way to try to mitigate some of these extreme, heavier rains and things. I mean, if you're using no-till or cover crops even to protect against erosion, or soil structure, improve soil structure for infiltration. So yeah, those are ways you could try to alleviate some of the impacts of some of these kinds of events. I was going to talk about Tropical Storm Lee as kind of an example of an extreme event that we had. These extreme events, they happen, and they happen even in the absence of climate change. We get them, and so, but when they do happen, they can cause, quite a bit of challenges. This shows Tropical Storm Lee's trajectory right through the heart of central Pennsylvania, and there's Mantango Creek right there. We got about 12 inches of rain in 4 days from Tropical Storm Lee. And stream flow was the third highest that we've seen since the late 60s. Only Agnes and the flood of 1996, the winter rain on snow flood that we got, were higher than this one. Lee was kind of an interesting event, actually. It was driven by an atmospheric river. So this just shows kind of the trajectory of storms prior to Lee moving through Pennsylvania. And it's just to point out that so here's a hurricane. This is Katya sitting out here in the Atlantic, and here's Lee making landfall on the Gulf Coast. We can kind of put this in motion, and you can see how right here at the end you get this interesting phenomenon. We get these connections between the Gulf of Mexico and the Atlantic, and this hurricane actually feeding moisture into Lee. So these are called atmospheric rivers, and this is what drives some of our most extreme rainfall events that we get in Pennsylvania. In California, they depend on atmospheric rivers for their wintertime precipitation. It's what really brings a lot of their rainfall, and even in Europe, same thing. But when we get these kind of atmospheric river types of events, they can really ramp up the extreme rains. Some of the extreme rains they had in Ellicott City, Maryland, actually were also, I think, driven by moisture inputs from afar. There was some extreme rainfall that happened in Philadelphia, Baltimore, and up on Long Island. I can't remember the year, maybe 2013, and it was also driven by an atmospheric river feeding into these thunderstorms, and they just kept receiving moisture and dumping more rain. So these kinds of events are what causes some of our real extreme rains. Now, interestingly, when we look at, say, and we do a lot of water quality research in our watersheds, and so we looked at the phosphorus data that came off from Lee, the amount of phosphorus that we lost in runoff from this one storm. And so here I'll just show you, for Tropical Storm Lee, we lost 6.1 kilograms. I'm sorry, these are in metric units. I'll have to convert them to pounds, but 6.1 kilograms of phosphorus came off just from Tropical Storm Lee. If we look for the entire year of 2011, that actually was 63% of all the phosphorus that we lost in 1 year came from that one storm. So that one event, the majority of the phosphorus that came out of this little watershed came from one storm. If we look across the entire decade, Tropical Storm Lee accounted for 21% of all the phosphorus loss that we've seen over the last decade. So the amount of nutrients that were moved, more than likely sediments followed about the same trend. We lost a lot of stuff because it was just such an extreme storm that activated a huge part of the watershed. A lot of the watershed was generating runoff even farther up into these, drier areas that normally don't produce much runoff. But in a storm like Lee, there was quite a bit of flow. And the interesting thing about storms like Lee is, it really is the antecedent conditions that matter. So, how wet or dry it is prior to the event. So, we get these interesting relationships that we see when we look at data, when we look at how much water, this is the volumetric water content, or soil moisture, if you will. So how much water is in the soils, how wet or dry they are. So you hit about 25%, which is not just about field capacity for our soils. And all of a sudden there's this threshold. and you get above 25%, all of a sudden a larger fraction of the watershed can contribute runoff. So this event runoff coefficient here can be interpreted as the fraction of the watershed that's actually producing runoff. So, so it's just 0.1 would be 10% of the watershed's producing runoff. 0.2 would be 20%. So Lee, up here, let's put this, here's Irene, which is a predecessor rainfall event. And actually, this is the interesting thing about this particular storm is that Irene wetted up, and then Lee came along 2 weeks later, and with 12 inches of rain, all the soils were really wet, and you produced a heck of a lot of runoff. 30% of the watershed was generating runoff, whereas events down here, even with 4 or 5 inches of rain, almost no runoff really happens because the watershed is so dry. So the response is quite a bit different. And as we move forward with climate change, this is actually going to be an interesting thing because they really haven't seen a big uptick in flooding in a lot of the streams in Pennsylvania, even with all the increased rainfall that we've gotten, because a lot of the rainfall increases are happening in the summer when the soils are much drier. So we haven't really seen a response in flooding like we've seen the rainfall. So the rainfall's gone up, but the flooding hasn't really followed suit. And as you go into the future, it's going to depend on when these extreme rainfall events happen and how wet or dry the soils are. And if they're happening in the summer, it's more than likely that the soils will be drier and that flooding might not be as bad, even though you get the extreme rains. So that'll be interesting to kind of watch, I guess, as we move forward. So Tropical Storm Lee's rainfall was quite extreme. It was basically a 300-year event. But what about some of these other events that happen more frequently? Even their frequency is changing, where now what would have been maybe a 100-year event, maybe in the 1950s to 1970s is now considered a 60-year event. So what would have been an event that would have happened maybe with 1 in 100 probability is now a 1 in 60 probability. So these kind of extremes are coming more regularly than they used to, and we're seeing that even in our own watersheds. We're seeing fewer days with snow on the ground, so that's also a big trend in the Northeast. We're seeing fewer days with snow on the ground, so those are just the number of days where there's any kind of snow on the ground, and that is going down by about 1.9 days per decade. And we're seeing more winter precipitation falling as rain. So basically that just means more rain than snow, even in the winter. So I mean, even though we do get snow in the winter still, a lot more of that is coming as rain. And that trend is common throughout the Northeast, especially in New England. They've seen steeper trends in rain versus snow. And so consequently, we've seen a real big decline in snowmelt runoff floods. We used to get quite a bit of these where you have snow on the ground and then it rains shortly thereafter and you get a big flood. These are just us counting the number of floods that we had due to snowmelt versus the number of floods that we've had generated by rain. The orange bars show the rainfall generated floods, so we've had as many as 9 in the 70s, but not much change. And from year to year, there's not as much change as we see with the ones generated by snowmelt. So we had 7 in the 70s, 5 in the 80s, and then only 1 in the last 2 decades. So we've seen a big drop in the number of floods, and that's just essentially due to there's less snow on the ground and and less likely that you're going to get a rain on snow event to generate significant flooding. Doesn't mean it won't happen, but the probability is less. So climate change is definitely here. At least all of the results that we see jive with what the scientists from NASA and NOAA are reporting in the national climate assessments. We see rising temperatures, we see changes in ET with increases happening there, more intense rainstorms, and fewer snowmelt events. So I mean, just kind of changing climate conditions that we're seeing. And so now I'll try to give you a sense for some of the projections that are out there. I always begin with this. This kind of puts climate in a much longer term perspective. This takes advantage of a lot of climate reconstructions that have been done. But this green area are temperatures that we've had for all of agricultural history. So this is really where this is like the sweet spot for agriculture. We don't have much change in climate. It's stable. It's easy to kind of predict from year to year. If you get much above an increase from like 1 to 2 degrees Celsius, these are changes that humans really haven't experienced over the last 20,000 years. And then you get above 2 degrees Celsius, you've heard this in the news, I'm sure quite a bit, but the 2 degrees Celsius is kind of this threshold that we really don't want to cross in terms of climate warming. And so we kind of put on the bottom axis here, the last ice age, when agriculture first came around in 10,000 years ago, the intensive ag that came around 6,000 years ago, and then where we are right about now. And these are ice core and ocean sediment reconstructions of temperature. You can see us coming out of the ice age here into this green spot. And then for the past 10,000 years or so, we've been in this green zone, this kind of zone of not much change in temperature. And that's where a lot of agriculture has kind of come about. But the projections going forward for climate change, at least the worst case scenarios, look a lot like this. If changes in emissions were to occur, they would look more like the purple line. And so these are the challenges we face going forward, like rapidly changing climate and how do you adapt and adjust to conditions that are constantly in flux, as opposed to a period of time when climate wasn't changing very much at all. And so we've taken data from climate models. These are the global models run on grids like this. They're really coarse. But we take advantage of folks who can downscale these and basically just put them in finer resolution, so we can kind of show you the spatial trends with more detail in the Northeast. And we've used these 9 climate models. These are recommended by Catherine Hayhoe. She's a climate scientist from Texas Tech. So this is where we got the data. I can show you that we'll start off with temperature. So our climate in the Northeast is quite temperate. We have these nice range of temperatures from about 40 to 58 degrees. These are annual mean temperatures. As we move through in the mid-century, we get into, say, like the 2050 time frame, our temperatures are likely to go up. These are just annual means, but we're going to see about a degree or 2 Celsius increase or several degrees Fahrenheit increase in temperature, depending on where you are in Pennsylvania. And like as I've said before, a warmer climate means more extremes. So we can look at, say, a metric like days over 95 degrees Fahrenheit. And this is just taking downscale data for the watershed where we work, the Mantango Creek watershed. And you can see how that's projected to change as you move forward in time. In the 1970s, we might have had 2 days over 95 Fahrenheit. By the 2050s, the models project maybe 10 days over 95 Fahrenheit. And if you get to the end of the century, upwards of 35 days over 95. So this is a good indicator of the kind of the extreme heat that might come about, as climate change progresses through the end of the century. The New York Times has this really nice animation showing how 95-degree days are likely to expand, and you can see them kind of pushing up, into the eastern U.S. Areas where we're really not used to seeing much above 95 most of the time. Now we could be looking at 20 or more days per year of 95-degree temperatures if you get out towards the late century. So growing seasons are also going to change. Our growing season probably is maybe 195 days, give or take, or 200 days long in Pennsylvania. We could get out to 240 days going out in the middle of the century, and we can show you for Mantango Creek, that's pretty much an agreement. We kind of more in the 200-day time frame here, in the 70s, and as we get out to the end of the century, we could be at 250 days for a growing season in Pennsylvania. And growing degree days are likely to rise as well, just with increased temperature. So these are the accumulated growing degree days in Fahrenheit. So we're looking, most likely to see a response in growing degree days, upward trend. It could be 1,000 more degree days even by the middle of the century relative to where we are now. Days with frost are likely to go down, so just fewer days with frost because of fewer colder temperatures. And the plant hardiness zones are likely to continue moving northward. So this shows the USDA's current plant hardiness zones map, the one that was issued just a few years ago. And this will show you, I zoomed in on Center County so you can see the 3 hardiness zones that are pretty typical for Center County, 5B, 6A, and 6B. This is looking out just the next 30 years. So we're likely to shift up into a new plant hardiness zone, 7A, and we're likely to lose the cooler one, the 5B, is likely to kind of move further north and out of Center County. And if you get further out into the century by 2040 or 2069, based on some of the climate models, we could be looking at even a further shift and a shift into much newer plant hardiness zones as they continue to shift north. Our rainfall for Pennsylvania, we typically get, on the order of 42 or so inches per year of rain on average, and that's likely to go up to about 44 inches per year. And so we're looking at, a 10 to 15% increase in annual rainfall as we move forward in time. And Some of the extreme events, like so for example, the days of 1 inch of rain or more will tend to become more routine. So we'll get 5 more of these days, maybe by the 2100s. So 5 more days per year with, with 1 inch or more of rain than we used to get. We'll also see more frequent 20-year storms. So these are the ones that might bring about 5 inches in a day. So there's a 3-fold increase in these kinds of storms projected through the end of the century for the Northeast US. But kind of a paradox of climate change is that even though we're going to get more rain, we're going to be subject to just the increased temperatures, which are going to drive evaporation and potentially be drying soils. And so this is an interesting visualization that NASA did based on a study looking at drought, increased risk of drought. And so these are just this is soil moisture basically. So bluer colors are increases in soil moisture, and brown colors are decreases. And this is just going through 2100. So you can see how drying spreads all across the country. And in particular, the Southwest is going to dry the most, but even in the humid Northeast, we're looking at drying. So you're going to be kind of dealing with drought. At the same time, you're going to be dealing with more extreme rains and potential increases in rainfall, but longer periods of time when you've got drier conditions to compete with. And so I've used this in the past, and it's just kind of a nice animation that shows how Pennsylvania's climate is likely to change as you move to the end of the century. Basically our climate is on the move. And this just shows for eastern Pennsylvania. This is based on union and concerned scientists using data from the climate model showing that eastern Pennsylvania is likely to shift kind of to more like central Maryland, moving into 2010 to 2039. You move a little further in time, it looks a little bit more like southern Virginia, and by the end of the century, absent any major changes, you're looking more like southeastern Georgia in terms of what the climate's likely to be like. For western Pennsylvania, it's kind of more of a western Maryland feel. Then, by mid-century, it feels a lot more like today's central Kentucky, and by the end of the century, climate is likely to be a lot more like today's northern Alabama. So big changes, assuming no major changes in emissions. So where can you go